get the slideshow set up.
And do you have a lab today in your physical science?
Yeah.
Once this finishes, I will help you with that.
Okay. And actually, how are you at tying knots and threads?
Depends on what kind of knot you need.
Just any little knot to hold it. But I have such thumbs.
Your fingers are very wrong. Mine are pretty articulate.
Okay. I might have you doing a couple of those because that's part of the lab today is Newton's laws. All right. We left off on page 134, section 4.3, example 1C. And let me get my pen back. Okay. Y double prime plus 4y prime plus 7y is equal to 0.
Okay.
All right.
And we're going to set y equal to e to the mx, right?
Yeah, e to the mx, got it?
Trick we're using right now.
Right.
Okay, so
And when it works a few times, you call it a method. Right.
right. It has worked a few times.
Right.
So our little method here. We're going to take first derivative that's e to the mx. Have it on this page.
Right.
And then m squared e to the mx.
Right.
Okay.
So,
And plugging that in the formula would be, and pulling out e to the mx.
right.
E to the mx times m squared plus 4m plus 7 equals 0.
Right.
Okay, and since e to the mx doesn't equal 0, we're going to want to factor, can we?
No. 7 is a prime number that will only be a.
If it was a 6, we might be in luck, or a
Yeah.
8, but
Yeah.
no such luck.
No.
So we get to use the old quadratic formula.
Right.
So that's minus 4 plus or minus, or wait, do we have to break this
Yep.
up into 2 or no?
Yeah.
Square root of 16 minus 4 times 7 all over 2.
Yep.
Okay, well, 16 minus 28, that'd be negative 12. Oh, man.
Yeah. One of those. Is that what you get?
Yes.
Okay. Now,
And this is where we got to do something a little different.
Yeah. but what we've done it, so now we just plug it in, basically. Okay?
Back into the one.
Yeah. This is what we were calling our alpha, and this is what we're calling our beta. Okay? So from what we had before, our y is equal to,
Okay, y equals C1, right?
okay. Now remember you got the alpha goes with the e. Yeah. It's e to the alpha, so minus 2 x. Okay?
And do we want to pull that?
Wait, okay, I'm sorry. C1, I forgot my
Yeah, I
constant.
said C1 and I was like, okay, is there not a C1?
No, yeah, there is. But actually, no, I messed up. I mean, I was looking at the wrong thing. I had started to said no, I want the e out there, and then I forgot. I said I wanted the e out there. I do it like this, or the e to the minus 2x, then C1.
And this would be e to the plus beta?
No, okay, yeah. Now, if you did that, you did, but you see what our result was from before is equation 8 above. There's your e to the alpha x. Our alpha in this case was minus 2. And then it's, yes, C1 cosine And the beta here is the square root of 3x plus C2 sine square root of 3x. Okay? Where the beta is the imaginary part and the alpha is the real part. That's it. That should be what they have here. E to the minus 2x times C1 cosine root 3x and plus C2 sine root 3x. Now, be careful. I think you said you typically did this. What did you call it? Bringing down the house or something like that?
I don't know what I call it. It's like
Yeah.
a roof or something.
Yeah. And
closing the garage door.
yeah, something like that to make sure that the x you don't think is inside the radical. It's not. It's outside. So so the A example there gave us two distinct real roots. Those are the m's.
That's fine. And then the second one gave us a double root.
A double root.
And then the x in the second term went before e.
Yes, exactly. The first one was just an e, very similar to the other, but the second one had an x in front of it with the same argument for the e.
And the third one is here.
And the third one, then using Euler's formula, the e to the minus, e to the imaginary part turns into a cosine sine. Which, if you did some fiddling around with it, like going back and checking each of those, you see how they make really good sense. Because this has a sine and cosine in it, and when you take this is the y, then when you take the y prime, you get a minus signs and a cosine, and then root 3s and things like that. And then when you do the y double prime, you get minus cosine and minus sine with your coefficients and that kind of stuff. And when you combine all those together, they sure enough go to 0. Okay. And you'll see that that's why this works well with that. Because you see, all those are pluses. You need something to get minus. That's why e to the mx just isn't going to work, because you wouldn't get any minuses there anywhere. Okay? Except possibly if the m was negative. But that just won't even be enough to get you there anyway.
It would have to be.
Yeah, it would have to have some negatives in it, and you don't have enough to do that. That's what this is telling you. Whereas the sines and cosines, they flip-flop, plus, minus, so. Or plus, minus, minus, plus, minus. Yes. They do a strange flip, but they do it. Okay. Let's do example 2, where we get to actually figure out what those c's are, because we're going to have some initial values. Let's solve this one. 4y double prime plus 4y prime minus plus 17y equals 0, with the initial condition that y of 0 is equal to negative 1 and y prime of 0 is positive 2, right? Okay.
Okay, so that's y equal e to the mx, right?
Yep.
So that would be 4m squared,
Right?
or well, plus 4m plus 17
Yep.
equals
Mm-hmm. Hang it up, Jack. M is equal to
C
16 times 17. What's that? 16 times 16, 256, and another 16 in there would be 272. I think it's 272, but I'm not sure. Check me on that.
Well, I mean, that would,
I'm not even sure 256 is right. It seems like it is, but it may not be. You don't have it? Oh, it's out. Okay.
because my good calculator, or my calculator that is working, isn't in my other bag.
Oh. 16 times 17.
272.
Okay. All right. Over 2 times 4. Right. Okay. Now, that would be minus 4 plus or minus. In fact, just to cut things down a little bit, let's go on and do.
That'd be negative 256.
Yes, it will.
Why
Exactly.
don't we just do that?
Why not? Okay. This is a minus 1/2. That's the minus 4 over 8. Plus or minus the square root of 2.
That'd be 16.
Wouldn't that be 16? Wouldn't it?
16.
Yeah, 16i. Or, yeah, 16i.
That's,
Well, 16 over 8i, so that would be 2i.
oh, wait.
Because
Maybe it's the 1/2 then.
minus 4 over 8.
Oh, okay,
This
you
over
broke
eight,
it
this
up.
over eight,
You
yeah.
broke it up.
Right. Because you're going to need those separately. The alpha and the betas need to be separate. Right?
I just, yeah.
Okay. So,
So, negative 1/2 is your alpha.
right. So it's the y is equal to e to the minus x over 2 times c1 cosine 2x, right, plus c2 sine 2x. Okay? But we know that y of 0 is equal to negative 1, and that would be e to the 0 would be 1. That's not going to give us much. Times c1, and cosine of 0 is 1. 2 times 0 is still 1, so that's a 1. But sine of 0 is 0, so that means c1 is negative 1, right? Okay? And we probably should have done this. Yeah, unfortunately we got to do that. So y prime is equal to product rule.
Whoa. That is unfortunate.
Yeah, right. Okay. Which you want to do first?
We'll do e first.
Okay.
1/2 e to the x.
Oh, so you're going to take the derivative of that first. Negative 1/2 e to the minus x over 2 times
That's
c1. Is that what you said?
Yeah.
Yeah, I know. That's what I said. I thought you said let's do e to the 1/2 first. I thought you meant by itself and then take the derivative of the second. Okay. Times c1 cosine 2x plus c2 sine 2x plus e to the minus x over 2 times.
Okay, so out front, we're going to have something. No, we're not. It's going to be inside that. Negative 2 c1 sine 2x plus 2 cosine 2x.
Right? Is that what you got? Okay. Now, let's pull the e to the minus x over 2 out of both of them. What you have here is a
Negative 1/2.
negative c1 over 2 cosine 2x minus C2 over 2 sine 2x minus 2C1. I hope I can, yeah, I think I've taken sine 2x plus 2C2 cosine 2x. Okay. Put a square bracket on one end and a regular on the other, it doesn't matter. Okay. Now, let's plug in y prime of 0, and that first one's going to be a 1, which doesn't really give us much. And this is going to be, and we know C1 is equal to negative 1. So that's a negative 1/2 here, right? Wait. No, it's a positive 1/2 because you have the minus sign and then you plug in a minus 1, so that makes it a plus 1/2. And cosine of 0 is 1, so that's okay. And then the next one goes away, the next one goes away, and then you have a plus 2C2. But cosine of 0 is 1. Okay? And this has to equal 2. All right? So if I've done that right, that would be 2C2 is equal to 1.5, right? And C2 would then equal 0.75. What's that?
Or 3/4.
Yeah, or 3/4, yeah. Let's see. Yeah, okay, good. Just wanted to check, make sure we're going right. So we go back into our original thing, and this will be e to the minus x over 2 times, I think I like to put the positive in front. So 3/4 sine 2x minus cosine 2x. All right. They, I'm sure, wrote it the other way. E to the minus x over 2, and they did the minus 2 minus cosine 2x plus 3/4 sine 2x. Yeah. Huh?
Where's the line?
Right there. I just put minus 7, although I like leaving off the side. And the minus sign drips down because my screen fell and it goes right in it. So. Yeah, it's a sad minus. Okay.
That's it. Why so negative?
At the bottom of the page, an interesting little topic, 2 equations worth knowing, as if none of the other stuff that we've taught you is worth knowing, but these 2 are worth knowing. I'm sure that's not what they meant.
If it's worth knowing out of what we've seen so far, it must be important.
Yeah, okay. Here are 2 differential equations. Y double prime plus k squared y is equal to 0. And the other being y double prime minus k squared y is equal to 0. Now, obviously from, I hope you see, from what we have done before, if we did the e to the mx thing, this would come out being m squared plus k squared equals 0. This would have come out m squared minus k squared is equal to 0.
That's just the
the first one. The second one would be a real case. Okay, because here, there ain't no real root there, but m is equal plus or minus ik, right? Yeah. Okay. Over here, m is equal plus or minus k. Okay? Yeah. So, what does that mean? The first case here would then be your real part is 0, so that would be y is equal to c1 cosine kx plus c2 sine kx. Okay? I started to put it in brackets of y. So,
C1 isn't distributed across.
yeah. Whoops, hit the wrong button. There we go. Okay. And in the other case, we have y is equal to C1.
Wait, because this is an imaginary case, it'd be the actual.
Yeah, the imaginary comes out sines and cosines, the reals come out exponentials. Right?
Yeah, because the plus or minus.
Okay. So those are, they say, worth knowing. Okay.
Yeah, I mean, it's kind of the same thing.
And if you think about it, what I was saying before is even more important here, because when you take y prime here, you get a k times a minus k c1k sine kx plus c2k cosine kx. Y double prime is a minus k squared, or c1k squared cosine kx minus k squared c2k squared sine squared x. And sure enough, the y double prime is k squared times this one. Because with sines and cosines, first time this changes sign, that stays the same, but they change functions. Next time they change back to the original function, but both of them wind up being negative. So sure enough, that is the case here. And over here, this is the exponential case. Yeah, e to the, first root here is c1k e to the kx minus c2k e to the kx. And the second root is c1k squared e to the kx minus which is plus c2k e to the kx. And sure enough, those are exactly k squared. The double prime is k squared of y. So, minus k squared. All right. Now, it says see problems 41 and 42. When you get back there, you can look at them. All right. Higher order equations. Okay. So let's clear this out of the way and see what we got here. In general, to solve an nth order differential equation where the a sub i's are real constants now, not functions, we must solve nth degree polynomial equations just like we did before. Okay? Now, if all the roots are real and distinct, then we get general solutions just like we did before with real distinct m's for your x's, for your e to the x, for your exponential functions. Okay? Now, the cases 2 and 3 are a little bit harder. I would contend quite a bit harder. And this goes back to pre-calculus, which you had in high school.
And I took 113 here.
Yeah, you had 113, but this was back in the algebra part. Yeah.
That's a long time.
Yeah. When you have a higher order, let's say, give me a higher order. Third, okay, cubed plus some constant. We can put a constant here. A plus bm squared plus cm plus d equals 0. Okay. Now, if life were nice and kind, which most of the time it's not,
A would be 1, right?
it could be. Okay. That would make it a little nicer.
That's
But even if not, if you could factor by grouping, that wouldn't be a bad thing to do. But in general, that's not going to happen that frequently. I mean, it's pretty rare that you can factor by grouping. So basically what you wind up doing is going through all those little tests that you do to see what your possible zeros are. I don't know if you remember the Descartes rule of signs. Did you ever have that?
That's very distant memory.
Okay. That just tells you how many positive real roots and negative real roots you may have. Okay. Then we had the rational zeros test, where you did b over a and did all the possible factorizations you had there, and that gave you all your rational zeros. Okay. And if you could come up with anything that would be a 0, then you do synthetic division on that with that 0, and you get down to a quadratic, and then you see if you can factor or use a quadratic formula.
Basically break it back down to quadratic.
If you can get that point, yeah. And you use those other techniques to try to find those roots. Okay? So that's what we're dealing with. Now here are some possibilities you could have then. Now with 3, it's not going to be that many. Let's get up to the nth order. Okay? So that one would be a sub n, m to the n plus, they're going back to a's. A sub n minus 1, m to the n minus 1, plus a sub n minus 2, m to the n minus 2, plus dot, 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 plus a sub, let's call it 3, m cubed, plus a sub 2, m squared, plus a sub 1, m plus a sub 0 equal to 0. I'll probably put more terms there than we really need. Yeah, I got sort of carried away with it. Okay, and you had all those there. If all those roots, in this case n of them, were real and distinct, then just list all those e to the blocks. Okay. But you might have some of those, and I don't know if you recall when you did your rational zeros test. Do you remember that one?
Like I said, it's distant.
Way back, yeah. You do a sub 0 over a sub n, do all the possible factorizations, and then just start testing. See, will this one work? And you do it with synthetic division most of the time. And if you got a remainder of 0, that's a root. But you don't stop there. You try it again, because you may have multiple roots of the same number. So let's just say that your roots here turn out to be what would be a good m, why not, minus c1 to the I, well, maybe not I. Let's use j, okay. And you also, these are all your factors, m minus c2 to the k times m minus c3 to the you keep on going. L plus times dot times M minus C. What do you want to call it? Second? We've already used M. We've then used N. We used N. I hate to use. I wish I'd have stopped sooner. But anyway, something. Why not A? No, we've already used A. B. Something. Okay, those are all the roots. Way up top, but not in the one right above it. Yeah. Okay. So you have all these factors. Now some of these could be ones here. That's fine. Some could be twos or threes or whatever. Then, and some of these are reals, and some of them are complex. In other words, got imaginary parts to them. So it gets really messy, okay? But really, you treat them each one separately. And if you have a multiple root here, what do you want the multiple to be? Pick a number. 3. Okay, so this is to the third power. And you want this real or imaginary?
Say imaginary.
Why would you say that? Okay, let's start with the real. That would be easier first. Okay, so this would be e to the cx plus x e to the cx plus, because you said you had 3 of these. So you're going to need 1, 2, 3. So it'd be 1 plus e. Huh?
You should probably write that.
Yeah. Okay.
That's a lot to visualize.
All right. Let's say you wanted that to be 3. That's a root, and we'll have a real root to the third power. So then that part here would be y is equal to e to the cx, c1x, okay? Yuck! I need something to call my constants. Let's call them k. k1 e to the c1x plus k2 x e to the c1x, just like we did before with multiple roots. When you had repeat double root, you did 2 of them. Now you got triple. So that would be plus then a k3 x squared e to the c1x. Okay? Now,
and then we divide that by the last term?
No. These, what? No.
That's something else.
No, these are the roots that you have. Whatever rational roots those were, they are it. That I probably shouldn't have used C1s, but I did, okay? Because a lot of books use that for a complex root. So let's say the next one here has, this is your imaginary part, okay? So what you want that C2 to be? You want it pure imaginary, or do you want it complex? Real and imaginary. I may be jumping ahead because they're not getting into those yet, are they? Okay. I may let me not get too far here. Okay.
Let's not dive into anything complex we don't have to.
Right. It is somewhat harder to analyze the cases 2 and 3. That's what I was trying to do here, because the roots of auxiliary equations of degree greater than 2 can occur in many combinations. Oh boy. For instance, a 5th degree equation could have 5 distinct real roots, 3 distinct real and 2 complex real roots, 1 real and 4 complex real roots, or 5 real but equal roots, or 5 real roots but 2 of them equal, and so on. There's just all sorts of, that's what I was trying to show with all those combinations there, okay? When M1 is a root of multiplicity K of a nth degree auxiliary equation, that is K roots of equal to M1, it can be shown, and this is what I was just doing, e to the m1x, x e to the m1x, x squared e to the m1x, up to x of k minus 1. We did 3, so we only did up to k x2. Now, I put the constants in there. They aren't putting them. Then the general solution would then put the constants in, but unfortunately, I was using C1s for my roots, and they are using C1 for the thing. They're using M1 for the roots. Yeah, I guess I should have used that. Okay. Finally, it should be remembered that when the coefficients are real complex roots of an auxiliary equation, always appear in conjugate pairs. When the coefficients are real, the complex roots are always in conjugate pairs. Thus, for example, okay, let's do this next one. That'll be easier than trying to imagine the cases with too much imagination. Okay. Y triple prime plus 3y double prime minus 4y equals 0. What's that? Yeah, you're missing a term there. Exactly. So what would be our, I always forget what you call it. Is it characteristic equation? Auxiliary equation. Auxiliary equation. What would that be?
MQ
Yeah.
plus 3m squared plus 0m?
No. Yeah, you can do that if you want to,
I
but
don't know if we need it or not.
yeah.
So plus 4, or minus 4.
Minus 4 equals 0. Now,
I didn't know.
okay. The easiest one to check to see if it might be a root, and this time it is m equal 1. Because then you just add your coefficients together. Right? Because if m equal 1, m squared equals 1, m cubed equals 1, yeah. So, when you add the coefficients, what do you get? 0. So you know right off the top that m equal 1 is a solution. Okay? Now, here's what I would do next. I don't know if the book's going to suggest it, but here's what I would do next. Take that 1 that you know is a root, and now do what you were doing. Write your coefficients down. This is synthetic division, by the way. 1, 3, 0, negative 4. Skip a line, draw a line, and start doing synthetic division. Remember it? Bring down the 1. Multiply. Multiply. Add.
Oh, 1 times 1.
Yeah, 1 times 1 is 1. 3 plus 1 is 4. 1 times 4 is 4. 4. 4, 0. That means your remainder is 0.
So that
That means it is a factor. We knew that. We'd already done it.
But we can do it again.
No. At this point, now when you get down to 3 here, plug it back in. This is m squared plus 4m plus 4 equals 0. Once you get it down to the quadratic, which is 3 terms, factor it. Or quadratic formula or whatever else.
So m plus 2 plus 2.
Yes, you got it. M plus 2 squared. There's your multiplicity. Okay? So it's m equal negative 2. That's a multiplicity of 2. This was your m equal 1.
Well, that's a double root, isn't it?
Yeah, and that's a double root. Okay? So here's what we do. For the m is equal to 1, your y equal c1 e to the x, that's for y is equal to 1, right? Plus c2 e to the minus 2x plus c3 x e to the minus 2x. Done. You got it. Okay? Yes.
That was,
Fun. Close to it anyway.
it was scary because it was easy. I
Yeah.
don't want to know what's going to happen next. They're going to go and ruin it.
Okay. So y is equal to c1 e to the x plus c2 e to the minus 2x plus c3x e to the minus 2x. Perfect.
Looking at example 4, I think they're working on ruining it.
Oh no, it just gets more fun. All right, to erase something?
Yep.
All
I'm
right.
going to miss it.
We're going to miss you when you're gone. Okay. Calais or something like that. d4y over dx to the fourth plus 2 d2y dx squared plus y equals 0. It's not nearly as bad as you're afraid it is. Okay?
Well, so the first one can be written as y
Fourth.
to the 4th.
Yeah. Well, fourth derivative of y. Yeah. Yeah.
But the second one, it can also be rewritten.
It's 2y double prime. Or, yeah.
Can
Yeah.
I do that?
It's easy.
I like the way it's written. I don't like Leibniz.
I didn't either. I like Newton. Okay, never mind. All right.
1, 2, 4, plus 2. Okay, so we can write this in M form.
M
So it'd be M to the 4th
fourth.
plus 2 M squared plus
Right.
M equals 0.
You got it.
Now, let's ruin stuff.
No.
We can do.
Don't ignore the obvious. The
-1,
easy. The easiest.
0.
No.
Yeah, 0.
What are you trying to do? Ultimately.
Find roots.
Factor.
Factor.
Right?
So we can factor this by grouping.
And what do you get?
M squared.
No, M. Factor out an M.
Oh,
M cubed plus 2m plus 1.
okay, so we know M equals 0 as a root.
Yeah, m equals 0 is a root, which is what you said before, but yeah, right. But factor it out and then do it. So m equals 0 is a root.
Right.
Okay, we'll get there. Okay, next one. That's a cubic. And oh, what a pain in the neck it is. Yeah, you're right. It's almost ruined it, didn't it? Let me make sure. No, I didn't think we were doing that right. That's not an M there. That's a 1 there. It's not y prime.
Oh,
Okay,
so
so
we
let's.
can't factor out M.
So we can't factor out an M.
That's going to change things.
But it changes it fairly much for the good, kinda, a little bit.
What can we throw in there to make that work? We need it to be a negative one. You can factor by grouping. That's
Not
what
grouping.
first.
Not grouping.
That is grouping.
M squared times M squared
Right?
plus 1 times plus 1. Won't that work? Okay. And,
Not minus, though.
huh?
Too bad they're not minus.
Too bad, but they're not. Okay. Make sure they're not. No, they're not. Okay.
Double check.
And this will be M equal plus or minus I. And this is M equal plus or minus I. Right?
I knew that.
Yeah. So,
Okay, so what we end up with is
y is equal to, you don't have a real part on that. It's e to the 0, which is 1. So that doesn't happen. So it's C1.
Or would it be C2?
You can start with any number you want to.
I mean, because if there was a real part to it, that would have taken the C1.
No, you don't. Remember, you only put the C with the sines and cosines. That part sits out by itself. Yeah. Okay. So
C1 times E.
the one sitting out by itself doesn't have a C with it. Okay. All right. So this will be.
E to the I, X.
Okay. But what did that come down to? When you had that,
Cosine.
that's your cosine.
Cosine of
X is your beta is 1. Okay?
plus cosine.
Well, let's not go too far.
C2.
C2, but you see that's a double root there. You had two i's.
X.
So then C2x cosine x plus C3.
C3? Where did C3 come from?
So-
There's multiple.
Yeah, there's 4 roots.
Four.
You got to have 4. Sine x plus C4x sine x. No. Wait a minute.
Is that
I forgot. Those should be minus x's here. Wait.
Cosine.
Yeah, no. I think that's right. Because they always come in conjugate pairs, so that it's plus or minus 1. So that's it. Let's see if that's what they get.
They got the middle two switched around.
Well, what difference does it make? It's commutative, isn't it?
Well, it's a cosine, an x times a cosine, and an x times a sine. Okay, yeah, we did that right. I was making
Okay.
sure that the x is out front.
There we are. I couldn't find the thing here. Yeah, they put the...
Cosine by itself, a sine by itself,
Yeah.
a cosine with an x, and a sine with an x.
Right.
That's,
So C1 cosine x, and what I said was C3 sine x, they put C2 sine x, plus C3x cosine x, which I put C2x cosine x, plus C4x sine x, which is what?
the first time I thought we just got, we had x's out in front of the wrong thing or something. But
Yeah.
we got it
Got it. Okay.
right. It's
So
still-
that wasn't nearly as bad
It's
as you were
still-
fearing it was.
It wasn't too
Right. Now,
bad. So,
example 4 illustrates a special case when the auxiliary equation has repeated complex roots, and therefore if M1 is equal to alpha plus I beta, beta greater than 0, meaning positive, is a complex root of multiplicity k, okay, of an auxiliary equation with real coefficients, then the conjugate M2 is equal to alpha minus I beta is also a root of multiplicity k, and from the 2k complex valued solutions, where k is your multiplicity, then you get e to the alpha plus I beta x, x e to the alpha plus I beta x, plus x squared e to the up to x to the k minus 1, because that was your multiplicity, e to the alpha plus I beta x, okay? And then you have the same things with the minus I betas there. We had plus I betas on the top, minus on the bottom. We conclude with the aid of Euler's formula that the general solution of the corresponding differential equations must then contain linear combination of the 2k real linear independent solutions. Okay? They're real now because you changed from the e to the I betas to sine betas. Okay, sine beta x. So you have e to the alpha x cosine beta x. If you had k roots, then that'd be x e to the alpha x cosine beta x, e to the x squared e to the alpha x cosine beta x, all the way up to x to the k minus 1 power e to the alpha x cosine beta x. Our alpha x was just a 0 here, so that's why we didn't have it. And then you do the same thing for the sines. Okay? In example 4, we had k equal 2, alpha equals 0, beta equal 1. So that's why you had 4 of them. You had 4 m's, so you have to have the 4. That's it. Of course, the most difficult aspect of solving constant coefficient differential equations is finding the roots of the auxiliary equations of degree greater than 2. For example, here's I have another one. Let me clear this so we can play with it a little bit.
It's funny because this isn't that hard.
No. This is where I wish we had been starting before when we were doing all that. Well, let's suppose this is a thing. Now, what's your other, you know? Why didn't they start this? That's how the book that I had before did. It skipped all that little, well, let's pretend, you know, and stuff, you know. It just went to this, and then all your constants show up. You don't have to. That's why I said, why don't they just show you how to get this, you know?
Maybe you should start chapter 4.
I'm wondering if I ought to write a book. You know, I wish I had my old one so I wouldn't have to, but, you know, this to me is, I don't know. So let's do, here's one. 3y triple prime. This is not an example. This is in the paragraph just past the middle of page 136. For example, to solve 3y triple prime plus 5y double prime plus 10y prime minus 4y is equal to 0. What would be your auxiliary equation?
Okay, that would be 3m cubed
Right?
plus 5m squared plus 10m
Right.
minus 4 equals 0.
Now, here's how I start on one like this. Nothing we can do to factor by grouping that'll make any sense, because it's an even number term, so I always look at that first. I don't see anything that'll work there. Then the next thing I do, would it be nice enough that 1 would work? No, it won't. Because you have 3 plus 5 plus 18 minus 4. That doesn't work. How about minus 1? Would that work? Now, with minus 1, it's almost as easy. You just change the signs of the odd power, the coefficients of the odd power, and keep them, yeah. The negative 3 plus 5, negative 10 minus 4, that won't work either. Okay. So then, what I do is go to the, well, you could do Descartes' rule of sign. How many sign changes you got here?
1.
1. That means there's only one positive real root. But there is one positive real root. Finding it may be hard, but there is one. Then for the second part of the Descartes' rule of sign, you do minus n. So this would be a minus 3m cubed plus 5m squared minus 10m minus 4. How many changes of sign you got there?
2.
Minus and plus, yeah. So you got 2 or 0 negative real roots. Boo hiss. You may not have any, but you could have up to 2. There's something wrong with that picture.
Well, no, because if you have 2 of that and then 1 positive, that would add up to be
3.
3.
No. Oh, yeah, and you got a total of 3. That's right. Yeah. Okay. So 2 of those may be complex, or 2 of them may be real. Okay. If they're complex, they're complex conjugates of each other, because these are all real coefficients.
Okay, so how do we get this?
So here's what you do next. The rational zeros test. You take the 4 over 3. It doesn't matter. You're going to do plus or minus there anyway. 4 over 3. And you do all the possible factorizations. That's all the possible factorization of 4. Plus or minus 1, plus or minus 2, and plus or minus 4. Your denominator, plus or minus 1, plus or minus 3.
I remember doing this.
Okay. Now, I like to start with the whole numbers because I like them best. Okay, you're not supposed to have favorites, but you do. So those are plus or minus 1, plus or minus 2, plus or minus 4. That's when you place them over 1. Okay? The not whole numbers are plus or minus 1/3, plus or minus 2/3, and plus or minus 4/3. Okay? We've already done plus or minus 1. They didn't work. Right? Yeah. Those are gone. Psst, sorry. The easy ones are gone. Let's try 2. Okay? So we'll try 2 first.
Are you trying it on the one with the M's, right?
Yeah. So then we'll do synthetic division of 2 into 3, 5, 10, and negative 4. Okay? Skip a line, draw a line. 3, 6, 11, 22, 32. No chance here. Definitely nah. Okay.
What about -2?
All right. We'll do that next. Ooh, it didn't work. Okay. Now I'm really lazy. So, yeah, you've noticed. Okay.
That's what I'm doing.
Put a minus here.
That's what I did.
Okay. And what do you get?
-6 would be -1, +2, 12,
Not going to work either.
-24,
Nowhere close.
Oh,
All right. So plus 2 and minus 2, they don't work either.
gone. And let's try 4, right? 4.
Yeah, that's what I was going to next, but I had to erase first. So plus and minus 2 are out. Let's try 4.
There's no way, Jack.
Huh?
No way. It's already getting
Too big. Right.
too big.
Okay. How about negative 4?
-7, +28, 38, no.
No. Okay. So it looks like it's down to the fractions.
Yay!
Okay. We love them. Okay.
1/3.
Let me get these.
6, 2, 12, 1/3, that's 4, that's 0, that's a root.
Really? 1/3?
It
Okay.
it works good because if you do,
Right.
that's a 1, you add that to 5, you get a 6, that's a multiple, you divide by 3, get a 2, get 12, that's a 4. It makes
Ding, 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 ding. We got a winner. A wiener. Okay. And remember, we only have one positive root from the calculus sign, so that's the only one here. But guess what? You're down to a quadratic, aren't you? Okay. So what do we have here? This is 3x squared. M, sorry. I'm used to doing the math. Okay.
It could be anything you want it to be.
Yeah.
It's football, but since we already used them,
Yeah. Good idea.
It would be fair.
Plus 6m plus 12. What's the first thing you notice you can do there? Factor out a 3. And then you have m squared plus 2m plus 4. And I think if you think about this too much, you can also notice that has no real roots. I don't think. Wait, it may have real. Well, let's do quadratic formula.
Plus or minus?
Yeah. Now let's start with a minus.
It would be
Minus 2 plus or minus the square root of
4
4 minus
or
16
all
over 2, which is minus 2 plus or minus the square root of negative 12 over 2, which is
got eyes in it.
minus,
Minus 2.
that's a minus 1, plus or minus, I'm taking that one out. But you can factor out a 4 out of that, right? Out of 12. That's going to be a 2i. So the 2 will go away, so it's I root 3. Okay. Our other two roots are this. Now,
Or this. It's not even, it doesn't even claim that's a number. It just says or.
okay. Remember that's a root. I forgot to write it down. M equal 1/3. Okay. So this is going to be, this would produce e to the minus x times,
Whoa, wait, why minus x up front?
what's that?
Why are we putting the minus x up front? Okay, so the minus 1 is that.
Yeah, that's the real part. Okay. I'm going to call this C2 if it's okay.
C2.
Okay, cosine
Root 3x.
root 3x plus C3 sine root 3x. There are the two roots from that one. The other one was that's why I reserved my C1 e to the 1/3 x, or x over 3. I think those are our solutions.
And that would just be added to.
What's that?
I was making sure it was just being added to what you had written
Yeah,
before.
right. It's another solution. Let's see what they got. They got y is equal to C1 e to the x over 3, I said 1/3 x, same type, plus e to the minus x without a constant in front of it, times, open parentheses, C2 cosine square root of 3x plus C3 sine square root of 3x. Yes. Okay. Now, there's a little blurb here on use of computers, finding roots and approximate roots of auxiliary equations, routine problem with the appropriate calculator or computer software, polynomial equations of one variable, degree, blah, 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 blah. So I'll let you read through that. Your calculation, your computer may do this for you. I don't know.
It would, I would.
Yeah.
No. It would. I would have to find something.
Oh boy, I'm wondering, could that be? No, I doubt it. It refers to a differential equation text by Ralph Palmer Agnew. That sure doesn't sound familiar, but it says used by the author as a student, gives a date of 1960. That would have been older than when I was in school. So that wouldn't be it. But anyway.
Whenever you said Agnew, I just thought of
Spiro?
Vice President.
Yeah, I thought of that too. Okay, sick minds. Okay.
What's funny is I think of them headless.
Headless?
Yeah, there's a cartoon type thing that depicted is supposed to be in the future and
Right.
preserved Nixon as a head and Agnew was a body and they still work together.
Oh,
It was just odd, but it's all like
strange. Mad Magazine, maybe? Okay.
Not quite.
Okay, all right. So homework exercises in 4-3, any of the odds 1 through 13, any of the odds 15 through 27, any of the odds 29 through 35,
Another section done.
either 37 or 39, do 41, try to, 43 looks like it's sort of fun, and or 45, and or 47, and then any of the odds 49 to 57, and I think that's all you'd have to do. All right. Now, we've got a little bit of time left, right?
About 8 minutes.
8 minutes. Okay, section 4 is undetermined coefficients, called the superposition approach.
First, I thought this was superstition.
Yeah. And 4-5 is undetermined coefficients with the annihilator approach.
Annihilator?
Yeah, exactly.
That sounds like it's either going to be a lot of fun or no fun at all. Depending on which end of the annihilating we will be on.
It says take your pick. And I think I've always gone with the first and haven't messed with the second.
What do you mean take your pick?
Between 4-4 and 4-5. They do the same thing. But
Let's see what
it says here this is based on the superposition principle for non-homogeneous equations, Theorem 471, which is way back. And it seems like that has more applicability, though I may be wrong. But it said take your pick which one you're going to do. And I've
the cool
just
name of 4.5 though.
almost begs for it, doesn't it?
Yeah.
And the other thing is it is a little shorter section, I think.
And if you haven't done it before, let's all do something new.
Okay. All right.
And if we hate it, we can always go back.
Having wasted that time. Okay. All right. In a sense, they should be fairly, in some loose type way, related, because they're doing the same thing, but they are just doing it in different methods. Well, that's what I was trying to determine. It just seems like the procedures of 4.4 are a bit more used. Remember when we did several sections ago and we talked about and fiddled around with the operator, D, capital D? That meant differentials, you know.
Yeah, it is. Yeah.
Yeah. That's what this one's using. Okay? 4.5. And
Since we stayed away from that, I guess.
I don't know. I mean, it's just, it almost comes out looking very similar when you're doing it. It just seems like the whole method is more familiar in 4.4, but I may be wrong. I mean, so you want to try 4.5? I'm not against it. I just hope it won't turn out to be too wacko. Okay.
Yeah, let's give it a shot.
All right. So we'll jump over to 4.5.
We only got 4 minutes. So.
Okay. We just wasted most of it talking about it. Okay. All right.
Have a meeting about the meeting.
Yes. The National Association of Organizations, right? Okay. Okay. When that was on Garrison Keillor. Yeah, it was Prairie Home Companion. When the coefficients a sub I, where I goes from 0 to n, are real constants now, undetermined coefficients, you assume they're constants. A linear differential operator, okay, which we have up above. Let's maybe write that down for now. An nth order differential equation can be written this way. A sub n, and rather than writing things in parentheses or ticks or tacks or whatever, we write it this way. D to the n of y plus a to the n minus 1, d to the n minus 1 of y, plus plus a sub, what did they go down to? 1. I was going to go down to 2, but 1 d of y plus a sub 0 y is equal to 0. Oops, nope, they're going to do a particular equation, g of x. Okay. That is your, I mean, it's the same thing as what we did before, where this stands for y to the nth derivative of y. This is the n minus first derivative of y, the first derivative of y, the 0th derivative of y. Okay. So it's just another way of writing. Okay. Now, when it suits our purpose, I love those kind of phrases. that equation is also written as some L of y is equal to g of x. You just write all those things up there as some L of y, which to me means linear operator, which means all these d's are to the first power, none of them to the second fractional or other powers. Okay. Now, where L denotes the linear nth order differential or polynomial operator, like I just said. Okay. Now, when this equation, this one that we have here, okay, are real coefficients, the constant linear differential operator here can be factored whenever the characteristic polynomials that we used before factors. In other words, if R1 is the root of the auxiliary equation, this auxiliary equation, a sub m in m to the n, that would correspond to this one, plus a sub m, no, n minus 1, m sub n minus, to the n minus 1, plus dot, 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 plus a1 m plus a0 equals 0. Okay. We've forgotten about the g for now. We'll pick that up later. That now is your nth order polynomial in m. Okay. In that. Okay. Now, so when we're dealing with the d's, you just treat those as if they were m's, basically. I mean, that's the same thing you're doing, okay? So let's say we had a d squared plus 5d plus 6 times y, okay? Now what that would mean was second derivative with respect to y plus 5 times the derivative with respect to y plus 6y. You know, that's what it would have been. That's what it is now. But these are operators. But guess what? We're going to factor them just like they were numbers. That would be a d times a d, a plus and a plus, a 3 and a 2 times y. So that means either factors of a linear differential operator with constant coefficients commute.
That equals 0, right?
Yeah, well, yeah, if that's what it was equal to, and up here it was, so if that's equal to 0, then this is equal to 0, then you could say d is equal to negative 3, and d is equal to negative 2. But these are operators, so what do you mean by that? Okay, that means, okay, that's where it gets a little squirrely, and maybe beyond where we need to take it, okay? But factors of a linear differential operator with constant coefficients commute, okay? Doesn't matter which order you do. D plus 3 times D plus 2 is the same as D plus 2 times D plus 3. Okay. How's the time?
We are over.
Over. Okay. Let's pick up then with that little sentence that starts a differential equation such as y double prime plus 4y prime plus 4y equals 0. We'll start there and try to play around with this a little bit. Okay? So that's where we'll end here. That is Tuesday's class, so you don't need to come Tuesday morning.